So today we are going to discuss Feynman path integral. So let me just first write it. And it is a very useful techniques for quantum field theory. So first of all we will understand what Feynman path integral is, and then we will try to calculate its mathematical things out of it. Okay, so actually here I am going to teach from the paper published by the famous physicist, that is the Richard Feynman itself. Okay, and the name of the paper is given by Space-Time Approach to Non-relativistic Quantum Mechanics. Okay, and it was published in 1948. So whatever I am going to discuss here, you can find from this paper. Okay, so first of all, what we do is consider a quantum particles, and this quantum particle is localized at some initial moment of time t0 in the vicinity of some initial point. Let's say this initial point v or I vector, and as you know, the quantum mechanical particles means it is equivalent to a wave packet, so we represent it by this symbol. So this is the initial positions Ri, and within this region, initially at time t0, quantum mechanical particle is localized. Okay, then we ask that what is the probability for this particle to reach some other point, that is we call it as a final point in time t, that is at time t0. If the quantum mechanical particle is in this position or is in this state, then we want to find out the probability of finding the particles or probability of the particle to reach the final point Rf. Okay, so here we denote this particle presence of the particles by its corresponding wave packets like this. Okay, so what could be its answer? Well, let me start with first classical mechanics part. So if this particle is classical particles, then it will follow the unique and well defined path, that is from the initial position to final positions. It always follows a unique and well defined classical trajectory. For examples, if I consider the free particles, then it will always follow a straight path like this. Okay, but according to quantum mechanics, or according to Feynman, the quantum particle goes all over the possible path. So for the quantum particles, there are infinite number of possible paths like this. It is from the initial position to another positions. Whereas for the classical particle, also we actually have infinite number of paths, but after extremizing our action, we actually get the actual path. It is for the classical particle, but whenever we consider the quantum particle, then Feynman says that actually for quantum particle, all paths are possible. Okay, that is not single trajectory for a particle. Also, he said that there is a weight associated with each trajectory. I mean, there is a way, or there is a probability of finding the particle, I mean here quantum particle, to propagate for a particular path is associated with each particles, and this probability is equal to I by h cross into s. Here s is the classical action. Okay, so s is the classical action. So I can write this action as starting if the initial at time t equal to 0 and then final time t equal to t dt into its Lagrangian, but we know that Lagrangian equal to kinetic energy minus potential energy, and this describes our classical action. Okay, so in classical mechanics, if we vary this action, that is delta x, okay, that is the minimum action, or minimize this action, then we get the Newton's equation of motion, right? This is for the classical particle, Newton equation of motion. Okay, but in quantum mechanics the case is completely different. That is, there is no principle of least action. That means there is no particular path that the particle follows. Okay, all paths are possible. I mean, all actions are allowed. Okay, and all of them gives rise to some value in quantum mechanics. That means each path has some probability. Okay, so now how to calculate the probability? I already have mentioned that each path has some probability, and this probability is proportional to e to the power I by h cross into its classical action, and we are going to prove it also. So I can write the probability of going from this state Ri to the state Rf for the quantum particle can be represented as sum of the all possible classical paths. So these are all the possible classical paths, and for the quantum particle, probability for going the particle from this initial position to final position is equal to the sum of the probability of all the paths. So I can write it as probability of the particle, I mean quantum particles, that it goes from the initial position to final positions can be written as this sum of the all path. So for all path, here I describe with the x e to the power I by h cross s of x. Okay, and as here we want to calculate probability, so and this gives the probability square. Okay, here s of x means action for the path, I mean particular path x. Okay, so and this equation gives the Feynman path integral formulations, and we are going to prove it. Okay, so this is actually the main theme about the Feynman path integral. So let me just repeat again. Classical mechanics says that for a particle to propagate from one region to another region, there must exist a unique path. Okay, But quantum mechanics says that all paths are possible, and each path has some probability associated with it, and this probability can be written as exponential of I by h cross into s. S here is the classical action. So the total probability of moving the quantum particles from the initial to the final position is sum of the probability of the all possible paths. So prove this thing. Let me start again and let me define, or let's try to understand something called the propagator first. Okay, so this is just a term for now, propagator. So let me try to explain this thing first. To explain this thing first, what we do is, so again here, let me just first simply copy it and just paste in this section. Okay, so here again consider the same quantum particles, and it is localized initially within this region at time t equal to 0. So time t equal to 0, the particle is localized in the region Ri. So, and initially this quantum particles has some wave functions. So we define the wave functions at time t0 is equivalent to these locations of this particle, I mean this state vector, position state vector. Okay, so here this is actually called the eigenvector of the position operator at time t equal to 0. Okay, or this wave functions is a very narrow wave packet localized in the vicinity of Ri. Okay, now we have our initial wave functions at these initial positions Ri. Then we can find out the evolutions of these wave functions, okay, by using the Schrodinger equations. So the Schrodinger equations is given as IH cross del t into psi state vector momentum, that is this term explains the kinetic energy term, plus potential, and it is function of positions vector, and again psi. Okay, so if we by solving these Schrodinger equations, we can find the evolutions of this state. That is, we have initially this initial state, and we want to find out the evolutions of the final state after some time t. And so actually the evolutions of this state or evolutions of this wave packet means the spreading of the wave packet in space. So here initially we have wave packets, and with due time these wave packets spread all over this place. Okay, now what we want to actually calculate is what part of this particle will propagate to the certain final region. That is, this is the certain final region. Or we can also say that what part of the spreaded wave packet will be located at this final point, this final region. Okay, so what we actually calculate is to calculate the part of the spreaded wave packet at this final region. What we have to do is we have to calculate the final wave functions or evolutions wave functions at time t, because we want to calculate positions of the wave packet at time t. That means to describe the system we need its corresponding eigenstate at time t, right? And then whenever we operate this eigenstate with this positions vector, then we can find its probability of finding or spreading of this wave packet or finding the particles at this final positions. Okay, so what we want to find is this r of f vector psi of t equal to what? Okay, this is what we want to find. Okay, now again we ask that how the particle will go from this initial point to the final point. In quantum mechanics, we can't predict the exact trajectory of the particles actually. As I already have said, there are all paths are allowed, and why all paths are allowed? It is because of the uncertainty principle. We cannot actually predict the exact path for this particle. Okay, because we cannot have a particular path. It is because of the uncertainty principle. Hence we will see that the particle goes from this initial position to the final point through all these possible paths. Okay, now for the probability of particle present at this final position, we have to first calculate these wave functions at time t. Okay, so let's try to do that first. So how can we find out these wave functions at time t? Well, we have our initial wave functions at time t0, and from this initial wave functions at time t0, by operating with our evolutions operator, I can get this the new eigenstate at time t. Okay, or we can also do the same by solving the Schrodinger equations. So let's see. So what I said is at time t0 we have our state psi 0, right? And I just write it in this format, psi naught at time t0, and it is equivalent to this positions vector. Okay, and I said that after some time we want to find this evolutions, how this state vector evolves. So the state vector at time t, we want to find out the nature of this state. Okay, to find this state, what we do is when we operate evolutions operator, and this evolutions operator is actually the function of time. This when we operate this evolutions operator on this initial state, then we will get its final state. So I can write this evolutions operator into this initial state equal to this final state. Okay, now what is the nature of this evolutions operator? Let's try to find out. Okay, how can I find out this thing? Well, if we put this equation in the Schrodinger equations, then we can easily find out the nature of this evolutions operator u. Okay, so we have our Schrodinger equation I h cross del t psi t equal to h psi t. Okay, so here instead of psi t vector, I can write this I h cross del t u equal to u vector, and here this psi of 0 is just a constant vector, so I can just take it out. Now by solving these equations I can find the value of this evolutions operator as e to the power I by h cross h t. Okay, so it is in exponential form. So if we have an initial state psi 0, then when we operate this initial state with this evolutions operator, then we get a new state after time t, that is the gate vector psi, which is equal to exponential of minus I by h cross into ht to get vector of initial state vector. Okay, this is what the expression looks like. Okay, now we actually want to find out these equations. Okay, now we have the informations about this term. So if you put this term, so I can write this term now like this. So r of f exponential minus I by h cross h t into this state. This is nothing but our initial state vector. So r of I. Okay, or this is the actual thing I wanted to calculate. Okay, or in more precisely I can write, and actually this actually explains the probability, or this actually gives the probability of spreading the particle at the final position after some instant of time t, right? So, or this is nothing but the amplitude actually. So amplitude, or g, we usually call it as the kernel also of the particle starting from the initial position to the final positions after time t is equal to r of Brouwer vector exponential I by h cross Hamiltonian into t, again final vector. Okay, this is the actual expression we wanted to calculate. Okay, so let me just write it in more user friendly way. So g of ri starting ri rf t equal to, here I consider this x of f as the final state. This is just notations, so not big deal, minus I by h cross Hamiltonian t xi. Okay, this is the equations. From now on we'll use this notation, but now notice that here this h, or this Hamiltonian, is an operator, and actually this term is in exponential form. Okay, so to solve this exponential operator in the matrix form is very much difficult. Why I say that we have to solve this in the matrix form? Because I can represent these state vectors xi and xf in a metric form, so I should also write the equivalent matrix form for this exponential term. But it turns out that, and then after that, by solving that, we should get our this amplitude, probability amplitude. Okay, but it turns out that this exponential, it is very much difficult to solve these exponential terms, these equations, because of the presence of this exponential term. Why? Because when we expand this exponential, when we expand the exponential form like this, we'll always get the infinite series like this: x prime, x prime square by 2 factorial, so x prime cube by 3 factorial, dot 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 dot. So this is an infinite series, and it is difficult to solve all this number. Okay, so how to solve this equation? And if we can find out another way to solve this equation, then our job is done. Okay, so here comes the trick. Let me just write this part first. Okay, so we have this term and we want to solve this term, I mean particularly this term. So how to solve this term? To solve this term, actually we need some mathematics. So let me just write that mathematics. I said that the state vector xi and xf are actually orthonormal vectors. Orthonormal vector means xi xf is equal to delta fi. Okay, so also this vector forms a complete vector. So xi must be equal to a unit matrix. Here I start from 1 to n. Okay, so this is in the discrete representation, and in the continuous representation I should write d of x xi equal to 1, and this is true for any kind of this positions vector, especially in this part. Okay, now let us try to understand our evolution equation first. That is, we have now our final state vector, that is the psi of t eigenvector, and it is equal to our evolution operator, which is function of time, and our eigenvector at initial time t equal to 0. Right, now let us try to understand the properties of this evolution operator. Okay, so for that, what we do is following. So let's just draw a straight line here and try to understand things. So initially at time t equal to 0, we were in the initial state, that is the psi of t, and as time goes on, after some time t equal to t, now we get the final state, that is the psi of t. Okay, suppose we divide, or suppose we want to find out our state at some other point, let's say t1. Then let's say at this time t1 we have our corresponding eigenstate as psi of t1. Okay, then if then I can write actually this vector as this thing as what? U of t minus t1 into psi of t1, right? So because anyhow we want to this state, initially we are in this state, as time goes on then we then get this state, after that this state, right? So if we trace back, then if we operate one more evolutions operator on this state, then we'll get this state, right? So I can also express this expression, I can also write this expression like this, but here we operated the evolutions operator this u equal to t minus t1. Okay, t minus t1 is just a time difference, like in this case t minus t0. Okay, just a time difference. Similarly here this is nothing but the t1 minus t0, that is the u of t1. So I can also write this as u of t minus t1, and I can express this term as u of t1 into our initial eigenstate. Okay, now by comparing this equation and this equation, I can write actually our original evolutions operator, or I can split this original evolutions operator into two parts, that is u of t minus t1 and u of t1 minus 0, that is t1. Okay, now let us try to understand this part more deeply. So we have one line starting from time t equal to 0 to the final time at time t equal to t, and then initially we had our initial state psi 0 to the final state psi, and we split. When we split once, we get two part, and for the two part we get two equations. Now what we do is, let's split into two equal part. That means at time t equal to t2, we'll get some other operator here, and at this region the evolution operator would be t minus t half, that is nothing but t by 2. In this part the evolution operator would be t half minus 0, that is u of t half. Okay, so when we divide our this timeline into two equal parts, then I can write our original evolutions operator as u of t by 2, again u of t by 2. So let us try to generalize it in more. So I can also divide this timeline in n numbers of equal part, right? So when I divide this time into n number of equal part, then this each equal part has some time, that is the delta time, t time. Okay, then I can write our original evolutions operator like this, right? So u of delta t by n or simply delta t, and it is n times, right? So u of delta t, and it is n times. Okay, now let us try to understand it more deeply, what actually happening here. Okay, so here let me just draw one more picture. So here we have time axis and the position axis. Okay, so what we do here is, suppose at time t equal to 0, initially the particle is in the xi position, right? That means at this position, and we want to find the position of this particle or probability of this particle at some other point, that is x of f at time t. That means this point. So we want to find out the probability if we have the particles initially at xi point at time t equal to 0, then what is the probability that the particles will present at this final position after some time t. Okay, so we found that there are lots of infinite number of possible paths, and all paths are possible according to quantum mechanics, right? And then what we did just before here, that we just split this time axis into n number of equal parts, and then before we split this time axis into two parts. So let's try to understand this thing first. Okay, here, so if we split this time into two parts, then I can just draw like this, and from this position to this position there are infinite number of possible paths, like this. Particle can go like this, like this, like this, like this, like this. All paths are possible. Okay, so I can also split this time into n number of equal parts, this, and there are n number of possible paths are there that we want to actually calculate. Okay, so now we have our this evolutions operator can be expressed in this format. We know that if we split our time into n very small n number of times, then each this delta time gives us the expressions about t by n. Okay, now what we want to calculate is following. So we have g. Okay, so we have this term, right? And this term is nothing but x of f u x of I. But here this u is actually function of time. Okay, but we just now discovered that this u function of time can be written as in this format, and here L delta t is very small actually, right? And so I can just write this equation in this format. So x of f. Okay, so now we have u of t equal to e to the power minus I by h cross Hamiltonian into t. So I can write this as when this operator for this small delta t, I can write it as I by h cross Hamiltonian into delta t, also e to the power minus I by h cross Hamiltonian t by n. But here remember that when n tends to infinity, that is means n is very large, then this term is very small. That means that we can expand this term in Taylor series, right? So if we expand this term in Taylor series, then this term becomes approximately equal to, I can write it as 1 minus I by h cross into Hamiltonian into delta t. Okay, and here we have ignored this higher order term. Now we have expression for u of delta t as 1 minus I by h cross into Hamiltonian delta t. So now I can write evolutions operator at time t equal to this u of t for n times. So I can write it as 1 minus I by h cross Hamiltonian delta t for n time, means to the power n. Now I can calculate our path integral, that is xf u of t xi, which is equal to what? I can calculate this, but before this let me just mention one more thing, that we have u of t equal to u of delta t, u of delta t dot 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 u of delta t, and here it is n times. Okay, now we also know that integrations of delta x into the state vector is equal to unit vector. Okay, so I can introduce this thing here, everywhere, like this, in between this evolution operator. Okay, one more thing here I should write, it should be delta t. Okay, so if you introduce this thing here, then I can write actually this equation as follows. So if you introduce here, starting from this final initial position, because here starting with here initial position, so this time the initial positions to the final positions, so this is the x1 into this x2 x1, and this term initial position is x0. So I can write this term as this. Let me first write this term. I can write this term as this thing. Integration for this term, this is k plus 1 term, so d k minus 1 x of nth term, okay, n minus 1 term, and for this term d, let me write in this way. So we will get, if we introduce in this part, we will get first x1, for next term we will get x2 dot 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 dot, for this term we will get x n minus 1 term. Okay, plus for all of this equation we will get, this is x of k plus 1 u of t. This is nth term, right? So nth term, n plus 1 term, and this is n term into xn u of, this should be delta t into x1 dot 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 u of x1, sorry, this should be xn u of delta t x0. Okay, but we know what it is, and we can generalize this thing, right? So if we generalize this thing, what I can write, let's see. Okay, so I can write this equation as follows. Okay, let me in this part. Now I can write x of f u of t I equal to integration d of x1 d of x2 dot 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 d of xn minus 1, because here all these things are the same thing, but starting from one to another I can just write in compact form, that x multiplication symbol from starting from k equal to 0 to n x k plus 1 into this state vector into what it is just this thing. So 1 minus I by h cross Hamiltonian delta t xk. Okay, here when k equal to 0 means it is the ground state or initial state, which is equivalent to Ri or xi, and x equal to n means it is equivalent to xi, or the final state. Okay, now you see that this term is no more exponential. There is no exponential, it is purely linear functions. Now we can easily calculate this term. Okay, so first of all, what we have to calculate from this equation? Well, first term I can see here, first term is 1, so I can write xk plus 1 into xk. I have to calculate this term first, and then second I have to calculate. Now see, these terms are just I by h cross and delta t are just a constant. So here h Hamiltonian is the only operator, and this Hamiltonian only operate on this state only. Okay. So we have to calculate this term. So xk plus 1 Hamiltonian xk, but we know that Hamiltonian is the kinetic energy plus potential energy. So this is the kinetic energy term plus xk plus 1 the potential energy term. But here this potential is function of positions only, so let's not worry about that. And this time, sorry, this kinetic energy is function of momentum. Okay, so to solve this thing, let me just first introduce one more thing. Okay, so now suppose if we have state psi vector and we have another position vector x, then we can get, when I operate this position vector x on this state vector, then I always get the wave functions for this position. Okay, similarly, when I operate this position state vector with the momentum state vector, I will get corresponding equations like this: 2 pi h cross root over e to the power I by h cross p into x. Okay, then when I operate this x position vector with another position vector, let's say x prime, then what should I get? Actually, I'll get delta function. Okay, so delta function, delta of x minus x prime. Let's try to understand this thing first. Okay, what actually it means. Suppose you have a basis, usual basis, that is e of I, and it is orthonormal. That means that e of I dot e of j equal to delta ij, and delta ij means it is equal to 0 when I is not equal to j, and equal to 1 when I equal to j. Okay, and sum of all delta ij equal to, so this is for the discrete basis. Now for continuum basis I can write, so for the continuum basis, this basis I can write this similar format, that is this vector or the inner product, we usually say it h delta function of x minus x prime, it is equal to 0 if x is not equal to x prime, and then it is what if x equal to x prime. Okay, let's try to figure it out actually what. Also this term, normalization term, I can write it as integration of dx delta of x minus x prime equal to 1. Okay, so what it actually means is this. Suppose this is some x-axis and this is some function axis. Okay, so what it means is these functions will exist. Okay, this is the x prime position, and this function will exist only at within this nearby region. Okay, so that is, if we draw its corresponding graph, then it will look something like this. Okay, only this is very small region, right? And if we integrate all over this space, then I always would get equal to 1. This is what it means. So now if I express this term in Fourier space, then I can write why I am expressing all this term to Fourier space. It will be clear in a moment. So in Fourier space I can write delta x equal to, starting from minus infinity to infinity, dk 2 pi e to the power I kx. Okay, actually this is k dot x, but k is along the x directions, x is along the x direction, so I'm just not writing that things. We just assume that. Also I can write this in this format, that is in terms of the momentum starting from minus infinity to infinity, 2 pi by h cross e to the power I by h cross p x. Okay, so now let us come back to our actual problem. that is we want to find out this thing and this thing. Okay, now I can express our this function, that is x of k1 x of k, as the delta functions, right? So delta functions of x of k plus 1 minus x of k, and in Fourier space I can write it as integration dpk minus 2 pi by 2 pi h cross dpk divided by 2 pi h cross e to the power I by h cross p into x k plus 1 minus x of k. Okay, and from now on I will write this term as delta x. Okay, similarly I can express the potential term, that is x k plus 1. This is the Bra vector of this potential term. It is function of positions only, and xk, and as it is a function of positions it will only give this term, and then again this term x of k plus 1 x of k, and it is nothing but our usual delta function. So I can write it as v of x integration dpk divided by 2 pi h cross e to the power I by h cross p delta x. Okay, now let us try to express kinetic energy term. In the kinetic energy term we have p square by 2m. 2m is just a constant, so I just have to write so this term p square term, right? So in the kinetic energy term we have p square operator, 2m is just a constant, so this. Now you see this state is the position state, this operator is the momentum operator. How can we operate? Because from uncertainty principles we know all this kind of thing. To do this, what we do is we write following things. We also know in the momentum space, if I write this completeness theorem, I can write it as condition this thing. Okay, so if I introduce this term here, then I will get something like this. So if I introduce this term in this region, then I'll get something like this. So integration dpk, this is x of k plus 1 p square by 2m. This is the momentum vector into x. Okay, and now this is just an operator which acts on this or operates on this momentum vector. Then I can just write it as p square by 2m, and it's this momentum vector. Now this thing is just a number thing. This is no more vector or no more operator now. Okay, so I can write or I can take it out from this bracket. So finally I will get dpk by, and actually one more thing I just forgot. I can write actually this in this format: 2 pi h cross p square by 2m e to the power I by h cross pk delta x. Okay, so now we have this term and this term. Okay, So then I can finally calculate our actual term, that is x k plus 1 minus I by h cross Hamiltonian delta t x of k equal to, or if for now I just ignore this constant term, then I can just write this proportional to integration dpk. And here notice that in all of these equations a, b, c, these exponential terms are same, so I can just take it out. So I can write I by h cross e of k delta x of k bracket 1 minus I by h cross, I can bracket ek square by 2m plus this potential, which is function of position, into this delta t, right? And now here notice that this term is no more now a operator. Okay, so now we can easily calculate it. Okay, and here also remember that delta t is actually t by n, and here n always tends to infinity, means when n is very large, that means this delta t is very small. Okay, so when delta t is very small, that means this term is very small. Okay, so I can just introduce, but we know that e to the power epsilon, where epsilon is very small, then I can express it as 1 plus epsilon plus some higher order term that we can ignore, and then I can write it as this thing. I can write it as this thing. Okay, here if I assume epsilon as minus I by h cross this thing, then I can express it. Okay, for examples, or so now we have our expression like this. We can ignore this term, and if I choose this epsilon equal to this term minus I by h cross this bracket term delta t, then I can express this whole term in this exponential format. Okay, so if I express this, I will get something like this. So this term is proportional to integration dpk e to the power I by h cross e of k delta x of k, again exponential, this term is minus I by h cross pk square by 2m plus v x of k delta t. Now you notice that this term is just looks like a Gaussian function, right? And we can solve this Gaussian function or simplify this Gaussian function, and if I simplify this Gaussian function, then I will get something like this. So we had x k plus 1 minus I by h cross Hamiltonian delta t xk. is directly proportional to, by solving that integrations we'll get exponential I by h cross m by 2 delta xk square divided by delta t square minus this potential term x of k into delta t. Okay, and this term is nothing but this velocity term. Okay, that is v of k, right? So this is nothing but our kinetic energy term, this is our potential energy term, and kinetic minus potential is nothing but our Lagrangian. So I can express it as exponential I by h cross Lagrangian, that is the Lk, into delta t. So this Lagrangian Lk is for a particular path k. So now we found that for delta t region, that is the small region, if we split, then we'll get this thing, right? But we put this equation in our previous equation, that is this equation. What is that equation? Yeah, in this equation here, then I can easily find out things. Okay, so if we put that equation in this equation, let's see what happens. So now finally we'll get our final state. Our final equation is x of f u of t x of I equal to integration del x1 dx2 dot 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 dxn minus 1. Okay, and all other terms are multiplied. Okay, so and each term is equivalent to this term, so e to the power I by h cross L1 into delta t e to the power I by h cross L2 into delta t dot 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 e to the power I by h cross L k into delta t, right? So I can write in this format. Also this thing, if I write in the compact form, then I should write in this format: del capital D of x into e to the power I by h cross summation lk delta t. This is k starting from 1 to n. Okay, and here this dx, this capital dx means this total term. Okay, this is just a shorthand notation. And here notice this as delta t is very small, so I can express these summations in integral format. So if I write this term in the integral format, then I can write it as e to the power I by h cross integral dt into its Lagrangian. So here this time starts from 0 to t, and this integral is over all the space, and actually this is nothing but our classical action, right? So I can write d of x exponential I by h cross into this classical action is s. Okay, so finally what we get is our transitions amplitude our transitions amplitude at positions x2 at time t starting from x1 at some initial time 0 can be expressed as this: integral over all path exponential I by h cross into the classical action. Okay, and this is what we call the Feynman expression for the Feynman path integral. Okay, we'll stop now.